one theory on some Euclidean four manifold with a U1 symmetry. And they argue that it's possible to preserve some supersymmetry on this manifold if there are solutions to some Killing spinor equation. And for instance, here is the Killing spinor equation for Z. And I argue that a solution to this equation can always be found on a complex manifold. So complex. And vice versa, the fact that M is complex is a necessary requirement to have the So given the fact that we have a complex manifold, we can then introduce we can put patches on the manifold and choose coordinates in each patch which are adapted to the complex structure. So we can choose coordinates in each patch, which we call W and Z, such that the complex structure has the form Gij equals I delta ij with the J bar component being equal to 0. And the fact that the metric of the manifold has to be a Hermitian is reflected by the fact that the only non-zero components of the matrix are the one with one holomorphic index and one anti-holomorphic index. And different patches on the manifold are related by holomorphic coordinate changes. Okay. So now if you remember the way that the complex structure was related to the spinor, we had something like J mu is equal to Ui. Okay. So now you can see that if I do an holomorphic coordinate change, J stays the same. So that means that the spinor Z can at most change by a phase. And then I can reabsorb this change of phase by doing a U1R transformation. So this is another way to say that the spinor Z is really a scalar under diffeomorphic coordinate changes followed by certain U1R transformations. And then the supercharge which can be built out of this, the supersymmetry transformation that can be built out of this spinor Z, and the corresponding supercharge should be really considered like a scalar under this holomorphic coordinate changes plus U1R transformation. So we have a supercharge, a scalar supercharge QZ, and this satisfies the following anti-commutation relation, so it squares to 0. And well, there are, in more special cases, there can be other supercharges corresponding to another spinor of this kind, of another like 1,0 spinor, or like some solution of the other equation we had yesterday, which was the one for the right-handed spinors. But in the following, we just consider the case where there is one supercharge.
So what does this equation ensure in terms of the complex structure?
Which equation?
The equation for Z.
This one?
Yes.
No. So okay. So what I said yesterday was that if you have one solution to this equation which is non-trivial, then it has always to be non-zero, because otherwise, if it's zero somewhere the solution is 0 everywhere. And then, like, from the solution, you can build a complex structure in this way, and you can show that this is a complex structure, so it satisfies, it is an almost complex structure, so it satisfies this equation. And you can also show that it's compatible with the metric. This is just by using field arrangement. And then you can compute derivatives of the complex structure using the equation, because basically they follow from the derivative of Z. And you can show by computing derivatives that this complex structure is integrable. So this almost complex structure is integrable, so it's actually a complex structure. Vice versa, if you start from a self-dual complex structure, you can show that this allows you to define some V by some equation which looks like V mu is equal to minus something like this. And once you choose this V, you can show that there is always one solution for Z on any complex manifold. So it's necessary and sufficient condition to have a solution. Okay. So there is a similar story in 3 dimensions, which I will perhaps review now. So in 3 dimensions, the equation that one has to consider is slightly different. So here I'm considering n equal to theories in 3 dimensions, again with type 1 R symmetry. So then the equation is slightly different, but similar in structure. So this is the same. This stays here. This is something like this. There is another piece. Okay. And again, here in 3 dimensions, the supergravity multiplet, besides containing the connection to the R symmetry and this conserved vector field V, also contains a scalar H. Okay, so we have to find 3 manifolds on which this equation can have a solution. And okay, so in the same way as before, you can see that like a non-trivial solution has to be everywhere non-zero. And then you can build out of this a vector field eta mu, which is just given by the following. Okay, so what you discover is that this vector field satisfies the following. So first of all, it has norm 1. And then, starting from this vector field, you can construct a tensor phi mu, just multiplying with the epsilon symbol. And this vector field, with this condition and the corresponding phi mu, define what is called in the literature an almost contact metric structure, ACMS. Which, well, the other equation that is satisfied is that
so are we in dimensions 3?
yes, 3 dimensions. Yeah, otherwise there is an equivalent definition, but in more than 3 dimensions, like you cannot relate phi mu to just eta in this way. So this equation is only valid in 3D. Okay, so these 2 equations are the ones defining an almost contact metric structure.
But is that the killing?
No, eta is not killing. So eta is a vector field which is everywhere non-zero, no 1. Yeah, it doesn't have to be killing. So what this structure gives you is that at every point I can split the tangent and cotangent space in like a part which is parallel to eta and a part which is transverse to eta. And then this phi mu acts as a complex structure on the transverse component. Okay, so actually this is not everything. What you can show starting from this equation is that this almost contact metric structure also has to satisfy some sort of integrability condition in the same way as the complex structure had to satisfy almost complex structure had to satisfy the integrability condition. So in the same way, this structure in 3D has to satisfy an extra differential condition which comes from looking at the equation. And this can be just written as phi mu times the z derivative along eta of phi is equal to 0. So basically what this equation is saying is that as you move along eta, the holomorphic, and you consider the transverse space to eta, then the holomorphic and anti-holomorphic sections of this space stays the same. So it is possible to show that once you have this integrability condition, then you can cover the manifold with certain adapted coordinates.
But how strict is this condition? Because almost contact metric structure is on for any orientable string manifold. This condition, how strict it is just to get any?
The short answer is that I don't know, but I have some more comments later. Just give me 5 minutes on this. So you can introduce adapted coordinates which have the following properties. So you can cover the manifold with patches where you introduce a real coordinate tau and a complex coordinate z. And this coordinate tau has the property that eta with upper indices is just equal to d tau. So the vector field eta is just equal to d tau. And the vector field dz is holomorphic with respect to this, is transverse to eta and is holomorphic with respect to this final view. And what is important is that if you consider two such adapted patches, because of this integrability condition, the transformation between the coordinates is that the new tau prime is just equal to tau plus a function of z and z bar, and the new z is an holomorphic function of the old z. So these are basically the equivalent of complex coordinates on 4 manifolds. You have these adapted coordinates for this 3D structure. So when we wrote our paper like a week ago, we asked some mathematicians if this structure had a name. So if this almost contact metric structure satisfying this integrability condition had a name, and we couldn't find it. But after we published the paper, we were informed that it actually has a name. It's called a fibration, a transversely holomorphic foliation of a 3-manifold. And it was actually studied by mathematicians in the mid-90s, and they actually found out a classification of the 3 manifolds on which this can be done. But I mean, I am looking at this right now, so I cannot say I understand this.
Naively, every cipher manifold has a structure.
Yes, every cipher,
So it is a statement that if you take a cipher, you can put an equal to with U1 symmetry.
Yes.
This is one.
Right. Actually, locally, you can, I mean, if you're not interested in global, I mean, there are global conditions and the mathematicians have studied this, but locally you can always like find out on any manifold which is orientable, you can find such a structure. Then the problem is like, can you glue it in such a way that it's globally well defined? That's complicated. Okay. And also, like the metric in this coordinate has the simple form. Let's see if I can write it somewhere. Let's get back here. So the metric is just given by tau plus some function h which can depend on tau, z, and t bar, and z plus h bar, z bar squared plus some function c which can depend on tau, z, and z bar times v, z, t bar. Okay, so this is, and you can actually show exactly as in the case of the complex structure that this is not just a necessary condition, but actually it's a sufficient condition too. That is, if you have almost contact metric structure which satisfies this integrability condition, then you can always find a Z which satisfies this equation. And more or less the proof goes exactly the same way. And again, the corresponding Z is such that if I do one of these adapted coordinate changes, by which the Z is transformed into holomorphic functions, and I follow it by a U1 symmetry transformation, then this Z transforms as a scalar.
Excuse me, is there a way you can start from a four dimensions in the
Yes.
setting you previously described and reduce to this?
Yeah, right. So I think if you have a manifold with like with a complex structure and a compatible metric which has a Killing vector, you can reduce along the Killing vector, and what you get is a normal contact metric structure which satisfies this integrability condition. So it can indeed be done. And actually, if you look at the examples of the classification of the manifold which allow for this, very often they just come from dimensional. Yeah, the description is just as a dimensional reduction of an appropriate complex manifold. It's basically the closest we can get to having a complex structure on a manifold, I think.
So this is not a structure which appears naturally on the boundary of this complex.
Yeah, no, I don't think so. Actually, I haven't thought about it. Not that I know of. Okay. So another question we are actually interested in is not just in coupling putting the theory, some supersymmetric theory on some curved manifolds, but because we already changed the metric, we can also like turn on other backgrounds for this theory. So for instance, if the theory has some flavor symmetry, so let's suppose, like for simplicity, that the theory has some U1, some abelian flavor symmetry, then this symmetry will correspond to some conserved current in the theory. Let's call it J mu F. And this current, because the theory is supersymmetric, will live in a supermultiplet together with a scalar and two fermions, J alpha and J tilde alpha dot. And in the same way as we couple the supercurrent multiplet of the theory to the supergravity multiplet, and then we froze the supergravity multiplet to some background values, we can do the same, and we can couple this current multiplet to a gauge multiplet in, which contains like a connection in U, let's call it in F. Then we'll have gauginess, lambda alpha and lambda tilde alpha dot. And there will be also a scalar, usually called D. Okay, in the same way as we set to arbitrary background values the bosonic fields in the supergravity multiplet, we can do the same for this multiplet, and we can set A nu F and D to be whatever we want, and lambda tilde to 0. And then we have to ask when does this choice preserve the supersymmetry that this supersymmetry parameterized by Z. And again, the condition is that this background this background choice should be preserved under supersymmetry transformations, which means that the variations of the gaugino must be 0. And you can work out the algebra and find out what this means, and it basically gives you two conditions. So the first condition is that F I bar J bar, so the field strength corresponding to the gauge field, with anti-homomorphic indices has to be 0. And the second condition is that D is given in terms of the field strength and the complex structure by this equation. So these are the equations that describe supersymmetric configurations of the background fields which couple to conserve currents. And
which dimension it is?
this is in 4.
Okay.
Yeah.
I'm confused here.
Right, yes, sorry, I'm going back to 4. Right. There is an equivalent thing, there are equivalent conditions in 3 dimensions. So in 3 dimensions, like you again have like a multiplet corresponds to a conserved current that you can couple to like a vector multiplet exactly in the same way. So this is a linear multiplet, and you can couple it to like a vector multiplet. Again, we find conditions which I'm not going to write down, but they're similar in spirit to these ones. And they describe supersymmetric background vector fields. Okay, so this condition here tells you that this AUF is part of a holomorphic line bundle over the manifold. So classifying the supersymmetric background gauge field corresponds to classifying the holomorphic line bundles over the manifold M into complex structure J. So in particular, like if you look at what, if someone gives you like some supersymmetric configuration of this this background gauge field, then you can ask like what are the possible deformations of this background choice, which still like are supersymmetric. And because you have to keep this equation, that means that your change in the anti-holomorphic components of this connection, let's call it delta and J bar, have to satisfy that di delta AJ bar minus dj bar delta J bar is equal to 0. But not all the delta AJ which like satisfy this equation are of interest, because some of them just like correspond to making like a well-defined gauge transformation in the manifold. And those are the ones for which delta I bar is equal to di bar of some well-defined like gauge parameter in the manifold. So you see that the like interesting deformations are classified by the by H01 of the manifold M. Okay, so this is like is what the kind of deformations of the background gauge fields we are interested in. Now what I would like to do next is just review some material on like deformations of complex structures. This is like what I would like to do, like the next hour, is trying to understand how the theory which we defined on this complex manifold actually depends on the metric and on the complex structure. So in order to do that, I have to like first review a little bit how the deformations of a complex structure look like. Okay, so so let's suppose we have a complex structure J mu, and therefore we can cover the manifold with morphic coordinate patches. And now we can look at like deforming this complex structure. So at the linear level, so we have J mu plus some delta J mu equals to J prime mu. And we would like this J prime mu to be like a good complex structure on the manifold too. So this like give rise to some conditions of this delta J mu. So at the linear level, which is the only thing I would be interested in, you get, so from the equation that J s to square root minus 1, you get that the components which have two holomorphic indices or two anti-holomorphic indices of this delta J have to be 0. So the only thing you are left with are the mixed components. And because the complex structure like is real, then you can just consider delta J ij bar. So up to now we just use this. Now you can also linearize the integrability condition of the complex structure. And what you find is like a differential equation for these delta J's. So at the linear level, again, this is just dj bar delta J I bar minus delta bar delta J I bar equals 0. Okay. So this means that if we define the object theta I, which is anti-holomorphic one form with coefficients in the holomorphic tangent bundle, by just putting delta J ij bar dc bar. So this is an anti-holomorphic one form with coefficients in the holomorphic tangent bundle. So then this equation is just that d bar of theta I is equal to 0, so it's d bar closed. But not all these deformations are of interest. Some of these deformations just come from doing diffeomorphism on the manifold. So a diffeomorphism is parameterized by a well-defined vector field epsilon mu on the manifold. And then we can compute the Lie derivative on, like acting on with this vector field on the delta J and compute, on J, and compute the ij bar component. And what we found is that this is just given by dj bar of epsilon I. So that means that the interesting deformations of the complex structure are given by d bar closed forms theta modulo d bar exact one form. So modulo theta I equals d of epsilon I, d bar of epsilon I. Okay, so that means that the deformations of the complex structure, at least at the linearized level, are parameterized by elements in the cohomology H01 with elements which are in the holomorphic tangent bundle E10. And the important thing is that these cohomologies are finite dimensional. So that means that we have for any compact manifold, there is some finite number of moduli which parameterize the deformations of the complex structure. And so this is just a condition at the linear level. At the non-linear level, there could be obstructions, so not all of these deformations would actually correspond to actual deformations of the complex structure, but we want to need this further refinement.
On Calabria, there is no problem.
Right. But in any case, we never have to go beyond the linearized level, so we don't care. Okay, so I set this up. And yeah, so the last comment I wanted to make is about compatible metrics. So given a complex structure, the metrics which are compatible with it are such that in adaptive coordinates they only have ij bar components, mixed components. So now we can ask, suppose we also change the metric. So what are the possible changes of the metric which are compatible with the complex structure? So that's easy. Like the changes of the metric which are compatible with the complex structure are just the ones for which delta G has only ij bar components, because if I don't introduce any completely holomorphic or completely anti-holomorphic components, the metric will stay compatible with the complex structure. And now we can ask instead, what happens if I do change the complex structure? So I introduce a delta J, and now the metric will no longer be compatible with J prime. So I have to change the metric in such a way that it stays compatible with the new complex structure. And so what we find out is that, again, in order for this to be true, the mixed components of delta J are arbitrary. You can take them to be whatever you want. And that's expected because this was already the case, even if I don't have the delta J. But the delta J tells me that I have to change the unmixed components of delta G in a particular way. So if I consider delta G ij, this has to be given by I over Q G I K bar delta J K bar J. plus G plus I, and there is like a similar expression for the one with two anti-holomorphic indices. So the delta J completely determines the change in the completely holomorphic, in the change of the metric with two holomorphic indices or two anti-holomorphic indices. Okay. Are there any questions? Okay, so next, what we'll do is something similar to what one does with topologically twisted theory. So there, one shows that there is some, so one has some suitably defined supercharge, which is a scalar on the manifold. And there is a suitable energy momentum tensor that one can show is Q exact. So it's Q of something. And these are statements that one can make even just by looking at the formations of the flat space theory, of the theory around flat space. And then this basically guarantees the fact that the supercharge is a scalar and the fact that the energy momentum tensor is Q exact. Basically guarantee that like the resulting theory is actually topological, so it does not depend on the metric. Even for fluctuations which are far from like being almost flat. So this is basically because, but it can be shown by using this effect that the supercharge is a scalar. Or like in a more systematic way, one could introduce like twisted variables. So like each field in the theory can be twisted and they give rise to like a different field, and then one can write all the theory in the twisted variables and show indeed that explicitly that it does not depend on changes of the metric. So here we could do this too, and there is a way to introduce like twisted variables and like make statements which are exact at the nonlinear level. But for the next half hour or so, I will just instead look at the linearized deformations of the theories that we construct around flat space. And from this, I will try to convince you that the partition function of this theory defined on some complex manifold only depends on the choice of complex structure on the manifold and not on the choice of metric which is compatible with this complex structure. And there is one important caveat that I have to make, is that all this discussion is at the classical level, so there, like in various cases, there could be anomalies entering, and I'm not going to discuss that. That's for future work. However, just let me say that there has been some work on trying to characterize the anomalies on the manifolds which allow for supersymmetry. And one thing that people have found is that in the case of manifolds which allow for two supercharges, each of with two opposite charge, then actually these anomalies vanish, so they're not a problem. Okay, so so we can. So what we'll do is we start with like flat space, and on flat space we choose some complex structure. There will be some complex coordinates, W and Z, and the corresponding complex structure. And then we will deform this complex structure, and because we deform the complex structure, we also have to deform the metric in this particular way, and look at how the theory responds to this deformation. So because of what I said yesterday, the deformations of the theory around flat space at the linear level are actually completely determined just by the structure of the supercurrent multiplet of the theory. So they are universal once one knows which supercurrent multiplet the theory has. So the first step in this procedure is that of understanding what are the supersymmetry variations of the supercurrent multiplet. So let's consider like a spinor Z which defines this complex structure, so for which the equation went away. So J mu is equal to I Z squared Z diagonal sigma mu Z. So we can consider one spinor which is true, and then look at the corresponding supersymmetry transformations in flat space, so which are parameterized by the spinor. And then we can look at how the various components of the supercurrent transform. So the various components of the supercurrent multiplet transform. So in particular, what one finds is that, well, this is expected. The variation of the undotted components of the supercurrent is 0. If you want, this is because Q anticommutes with itself. And then the interesting ones are actually the commutation relations with the other components of the supercurrent. And these are equal to the following. Where this object, curly T, is related to the energy momentum tensor. So it's given by the energy momentum tensor. This is curly T, this is the energy momentum tensor, and then there are corrections which have to do with derivatives of the arc current and other stuff. So for instance, you have something which looks like I over 2 d nu of j mu r, where this is the conserved arc current, and then there is other stuff. But the important thing here is just to recognize that if I multiply this, if I just multiply this by z without losing anything by zeta dagger sigma rho, then what I obtain over here is just a projector on the anti-homomorphic components of curvature. So from this, what you obtain is that all these operators T tilde mu with an anthropomorphic index in the second place are Q exact. They are Q of something else. Actually, because Q squares to 0, these are also Q closed. And actually, it's interesting to look at all the possible bosonic two-closed operators in the R multiplet. And what you find out is that these are actually all the Q-closed operators in the R. So all the Q-closed operators are actually Q-exact. Okay, so this is the first element in this story. Now the second element is to look at the deformations of G. Lagrangian. So we start from the Lagrangian in flat space, and then the deformations that we have had here are just given by the following. So we have the energy momentum tensor, which multiplies the change in the metric. And then we have these other auxiliary fields, which multiply the R current. And finally, there was also this operator curve A, which multiplies this background conserved vector field. And the important thing here is that given what we said yesterday, and now the equation, you can actually write down expressions for B and A at the linearized level. So for instance, let me just give you an example. You find out that like if you do some deformation of the complex structure and the corresponding deformation in the metric, the vector field V, the holomorphic components of the vector field V, are given by some expression like this, which depends on delta J and on the change of the metric. Delta G Z W bar minus Z W bar delta G Z bar. Okay, so there are some expressions that one can write down which relate these background fields V and A to the change in the metric and the change in the complex structure. Okay, so once you've done all this work, you can put everything together and you can rewrite this delta L explicitly in terms of the changes of the metric and of the complex structure. And what you obtain is the following. So you obtain various terms. Let me write some. So you have minus delta G I J bar, which multiplies this curly T I J bar. Then you get some pieces which can be written in the following way. So they also involve delta J I bar J times this curly tau J bar I bar. And all these terms are Q exact because they involve this curly T with an anti-holomorphic index in the second place. But then there are some terms which are not Q exact, and these are proportional to delta J with, for instance, there is a term which is proportional to delta J W bar, which multiplies the energy momentum tensor TWW plus I over Q delta mu R. And then there are other terms, one which is proportional to delta J W Z bar, the other one which is proportional to delta J Z Z bar, and delta J Z W bar. And each one of these terms is multiplied by some operator, which is not Q-exact. So because of this procedure, this Lagrangian is actually guaranteed to be supersymmetric. And indeed, you can take the variation of all these things. Okay, this we argued are Q-exact, so clearly like the variation vanishes. And then the rest, like you can compute the variations by looking at the variations of the energy momentum tensor and the R-symmetric current in the R multiplet. And once the dust settles, what you get is like a total derivative, which you don't care because you're integrating with a compact manifold. And the rest is proportional to d bar of this holomorphic of this anti-holomorphic form theta I, which has to be 0 because the deformation of the complex structure is supposed to be integral. So indeed, this was actually just a check because given what we said yesterday, the procedure was guaranteed to end up in a supersymmetric Lagrangian. And indeed, like you can show that that's the case. The other thing that you notice here is that all the terms are Q-exact, except those which multiplies delta J W bar, delta J with holomorphic indices up and anti-holomorphic indices down. So from this, you can say that the partition function will not depend on changes of the compatible metric. So if I change G I bar, I don't change the partition function because this multiplies a Q-exact operator. And it only depends on the variation of the complex structures holomorphically. So there is no dependence on delta J with an anti-holomorphic index out. So, okay, so this was a linearized analysis, but it can be made more precise, or one can use these arguments that rely on the fact that the supercharge actually transforms as a scalar under a suitable transformation to argue that this is actually enough also to nonlinear level. Okay, so this is the main result relating to the behavior of the theory under changes of the metric and of the structure. Let me just comment on something which is also trivial. Suppose I take one of these delta J's which come from an exact, a d-bar exact theta. So those are the delta J's which come from just making an infinitesimal diffeomorphism. So for those, there should be no dependence, because after all, the theory we started with is diffeomorphic invariant. And indeed, if you plug in delta J W bar, so if you just say delta J I J bar is equal to dj bar of some well-defined vector field, then you can plug it into this Lagrangian, and you can integrate by parts. And what you find out is that, again, like all these pieces can be rewritten in terms of all the pieces which are not Q-exact here, once you integrate by part and rearrange, they can be written in terms of this d tilde and therefore are Q-exact. So indeed, there is no dependence on the trivial changes which come from diffeomorphic, which, I mean, is just a check because it really was guaranteed by the fact that the theory we started with was invariant under diffeomorphism in the first place. And in the same way as you do this for changes in the metric and the complex structure, it's actually even simpler to check what happens if I have background fields which are background gauge fields which are coupled to conserved flavor currents. And again, exactly the same way, you can show that like the only dependence on the background gauge fields comes from like is holomorphic in the moduli which describe the deformation of these holomorphic line bundles. So basically, the end result is that the partition function should, bearing anomalies, should depend holomorphically on the deformations of the holomorphic line bundles coupled to the various flavor symmetries of the theory, and should depend homomorphically on the deformations of the complex structure.
Just more, you're saying that your partition function does not depend on the metric, right?
It does not depend on the metric. It does not depend on the choice of compatible metrics. So once I fix the complex structure, I have different choices of metrics which are compatible with this complex structure. The argument is that classically it does not depend on this choice of metrics.
But how does it depend on the scale, for example, right?
Right. So the
blow
scale,
up my volume.
yes, you can blow it. So classically you can blow it up and it should not change. So indeed, this is what happens, for instance, so in these cases which are two supercharges, so we can forget about anomalies. Indeed, you can show, like for instance, the partition function on S3 times S1, or version thereof, then you can actually show, you can actually see that what people compute does not depend on the size of the manifold. Now, when there are anomalies, it could be, for instance, that the partition function is just 0, because and then, like, I guess, if they say it's 3, okay, so this is for 4 dimensions, and there is a similar story which one can do in 3 dimensions, where one can show that the partition functions of this n equal to supersymmetric field theories on this almost contact, on these 3 manifolds which are an integral almost contact structure, does not depend on the choice of a metric which is compatible with this almost contact structure, but only depends on the moduli spaces of the almost contact structure itself. So I can explain to you personally, if you are interested later, how the formation of this almost contact structure work. But basically, it's the same result as this. It's obtained exactly in the same way. The only difference is that this structure is being somewhat unfamiliar, like it's a little bit more complicated to explain. But an important point also there is that for a compact manifold, the deformations of these integrable almost contact structures have finite dimensional moduli spaces.
Which exactly contact structures?
What?
What was your exactly last statement about finite dimension?
So if you take a manifold which is compact, a 3 manifold which is compact, and you look at the modular spaces of deformations of these integrable almost contact structures.
You mean integrable with
With
condition?
this definition of integrability, which has to do with this phi and its derivatives. Then you can show that these modular spaces are finite dimensional.
And it's controlled by which cohomology?
So you actually have to define, like, so for these manifolds there are some equivalents of the d-bar operator. I can show to you like how this works, but there is an equivalent of the d-bar operator, and then like it's controlled by forms which are like closed but not exact under this d-bar operator. So when we did this, we actually had various statements, educated guesses, saying that we think the cohomology of this operator should be finite dimensional, and we had some reasons to say so, but didn't have proofs. But now that we were informed of the mathematical literature, it's actually pretty good. Like they actually consider exactly the cohomology of this operator, and they show it's finite dimensional. So we don't have to. This is now. I can make these statements with being sure that they are correct.
But if you stay on cipher, for example, how much room for
yes, I don't know exactly. I know I know what happens in several examples. So, for instance, I know what happens on the manifolds which are diffeomorphic to S3. Then manifolds which are diffeomorphic to S3, there is a one complex dimensional branch of the moduli space, and then there are some exceptional points which are not in this branch, which are just points. So this is for manifolds which are diffeomorphic to S3. Then you can also make statements for manifolds which are diffeomorphic to S2 times S1, There it's a little bit more involved because you have two different, if you want, topological classes of these almost contact structures, and each one comes with its own deformations, which are also in this case one complex dimension.
And basically a statement that partition function should depend only on, should be functional.
Right, it's only depend, yeah, so for instance, one statement we can make is that if you take theories on manifold diffeomorphic to S3, they can at most depend, so on the main branch of this almost complex structure, they can only depend on one complex parameter. And indeed, you can actually show that all the deformations that have been considered in the literature lie in this main branch of the deformation of the round case. And you can map this parameter B that people found to like explicitly to this deformation. And yeah, so that you can be done for S3, and you can also do similar things for S2 10 + 1, where you can show that one of these parameters just correspond to the parameters that people have in the computations of the index on S2 10 + 1. Other questions? Yeah, I can say more about 3 dimensions in private. I don't think there is actually time to say it like this in 20 minutes. So instead, I would just wanted to give an example of this, and in particular, I think one very important example from which a lot of information about 3 dimensions can be obtained by dimensional reduction is that of off surfaces. So, okay, so now we are back in 4D. So off surfaces, or primary off surfaces, were studied by Kodaira quite extensively. And they are complex manifolds which are diffeomorphic to S3 10 + 1. So they are described in the following way. We have two complex coordinates, which we'll call W and Z. And these live in C2 minus the origin. And then these surfaces are defined by identifying these coordinates in certain particular ways. So we have two classes. There is class 1, which corresponds to identifying WZ with, I call them P and Q, with PW and QZ, where P and Q are complex numbers which satisfy the following inequalities. So they are greater than 0, and P is less than, P is less or equal to, the modulus of P is less or equal than the modulus of Q, which is also less than 1. Okay, so you have surfaces defined by these identifications. So the P and Q are actually the complex moduli of this surface. So you have a two-dimensional moduli space of different complex structures on S3 10 + 1. And then there is a second class of surfaces which are given by the following identification, which is slightly more complicated. So there is Q and W plus 1 and both. Okay, so Q and W plus 1 and QZ. 0 plus Q plus 1 and okay, so we have this N is like just it's just an integer greater than 0. And you can identify this complex coordinate in this fun way. And one thing is, well, you can show that this manifold is the resulting manifold is also diffeomorphic to S3 10 + 1. It seems here that also you have two complex parameters that parameterize these different complex structures. But actually this is not true because lambda is a fake. You can always set lambda to 1 by rescaling z. So there is actually only one complex parameter in this modular space, in this second branch of the modular space. Okay? So I won't say much about the second case, which is more complicated. What we have shown in our paper is that if you consider these complex structures on S3 times S1, then you can write down compatible metric for these, and you can show that none of this metric is compatible with more than one supercharge. So all of the metric compatible with this second choice only preserve one supercharge. And I don't think anyone in the literature has completed anything in this case. So well, it's for whoever wants to try. The first case instead is more interesting because one can make contact with objects that have been computed. So we can describe this manifold in some more familiar way by introducing some coordinates and rewriting this WZ in terms of angles on S3 times S1. So this can be done this way. So we have some coordinate x, which is identified with x plus 1. So this will be the coordinate, the angle along the S1. And then we have the usual coordinates, what they call them, phi, chi, which are in angles between 0 and pi. And then we also have a coordinate theta, which is not periodic. And so perhaps it's better to write this phi plus pi. Then we have a coordinate theta, which is not periodic. It just lives in between 0 and pi, on the interval 0 pi. And then we can rewrite these coordinates w and z in terms of these coordinates. So let's write p equals e to the minus beta p plus I theta p, and q in the same way we can write it as e to the minus beta q plus I theta q, where beta p and theta p and beta q and theta q are all real, and beta p and beta q must be greater than 0 because of this. Okay, so then we can write w equals e to the minus beta p plus I theta p times x times cos of theta over q times e to the I phi, and z similarly e to the minus beta q plus I theta q x sine of theta over q e to the I phi. And w bar and z bar are just obtained from this by complex conjugation. So because of this identification here, you can show that this corresponds to this identification. And hence, you have basically displayed quite in a primitive way that this is indeed S3 times S1. Okay, so now we have everything written in coordinates which are easier to understand. And you can write metrics which are compatible with this choice of complex structure. For instance, one metric, a set of metrics, I was just given by the following. X bar Okay, so for instance, you can take this metric. These metrics are clearly compatible with this complex structure because they only have W bar and ZZ bar component. You can it's also easy to check that if you do this identification, which corresponds to sending x to x plus 1, then indeed the metric is invariant. So they are good metrics on a strict and this one. And they are compatible with this complex structure. Yes?
I must have misunderstood the statement. I somehow presume that there is flat metric on 4, and you pull it back under this.
No, the flat metric
So
will not be compatible with the identification.
Then what is there is a unique metric compatible with this identification.
No, right. I mean, there is never a unique metric compatible with a certain complex structure. So I can choose. And I could put other stuff here. I mean, I could have a term which depends on dw bar times something else.
So what is
So this is an example of a metric which is compatible with this complex structure. The interesting thing about this metric, and the reason why I single it out, is that it has an homomorphic Killing vector, which is given by delta p w by anti-homomorphic Killing vector, whatever, the same. So there is an anti-homomorphic Killing vector. So by anti-homomorphic Killing vector, I mean something which is in 0, 1, and also all the coefficients are anti-homomorphic functions of the coordinates. And the one thing which followed from this analysis of manifolds which allow for supersymmetry is that if you have an anti-homomorphic Killing vector which commutes with its complex conjugate, then, in this case, the manifold allows for 2 supercharges of opposite R charge. So by displaying this metric with this anti-homomorphic Killing vector, which it's very easy to see, it commutes with its complex conjugate, this shows that every complex structure on this branch allows for a choice of compatible metric on which one can preserve 2 supercharges. In the paper, we show that instead, in this other case, there is no choice of compatible metric for which one can have such a Killing vector, and therefore they only allow for 1 supercharge.
It's supposed to be a 4 manifold.
Yes. So these are complex coordinates, dw bar, and dz bar.
And x.
What's that?
And x. You understand x?
Oh, x is just x is just given in terms of w and z. It's just that it's complicated to write x in terms of w and z. But in principle, I can just write w in terms of x, tet, and phi,
so x
and
is
z
not
in terms of x, tet, and chi, and rewrite everything, and I get a metric on a street and this one, which depends on this coordinate x, phi, and theta, and chi.
and x is supposed to be a global coordinate.
Yes, x is just the coordinate along S1. So I have the S3, and then there is S1. X runs along the S1, and the S3 is parameterized by theta, phi, and chi. So the S3 is given by ds squared is equal to d theta squared over 4 plus cos squared theta over 2 d phi. I hope the phi, I don't know if it's the phi or the chi, let me see. Yeah, I think that's correct. So this would be around S3 in terms of these coordinates, and then there is x which runs around. And okay, so if I add here plus dx squared, this will be the round metric on a street and this one. Instead, if I consider this round metric is not compatible with like any value of p and q.
No, maybe to have round metric, you want to have phases in W, phi plus chi, and phases in Z, phi minus chi.
No.
Well, Hopf vibration, we can talk about it.
Right. Okay, so the Hopf fiber would correspond to moving in d phi plus d chi.
Yes.
or d phi minus d chi, whichever way you choose. So these are not the coordinates around the outside.
And that's the isometric, so phi plus chi is supposed to be isometric directionally around. It doesn't matter.
Anyway, so like, the point I wanted to make is that every complex structure on this branch is compatible with having two supercharges. And then one can ask, when does it allow for more than two supercharges? So it follows from the analysis of the Killing-Spinor equation that you have four solutions only on the round S3 times S1, or on manifolds locally on the round S3 times S1. So you can ask, when does the round S3 times S1, when is it compatible with these identifications? And what you find out is that this happens only when the absolute value of P is equal to the absolute value of Q. So when the absolute value of P is equal to the absolute value of Q, the metric is locally the round S3 times S1. The complex structure is compatible with the metric which is locally S3 times S1. And this can be displayed explicitly by just changing its coordinates to phi tilde is equal to phi plus theta p x, and phi tilde is equal to chi plus theta q x. So the fact that the absolute value is the same means that beta p is equal to beta q. And once I do this change of coordinates, then, well, I could rewrite the metric that I have here, and it just becomes ds squared is equal to r squared beta squared ds squared plus d omega 3. So it is indeed the metric of around, locally it is the metric of the round S3 and S1. But one thing you have to notice is that these coordinates are identified in a funny way, because phi tilde, and x are identified as phi tilde plus beta p, chi tilde plus beta q, and x plus 1. So basically this gives you an idea of what this manifold actually is. You are taking S3 and you are moving it along the S1, and once, so first you cut the S1, so it's an interval, and then instead of gluing it together in a simple way, you twist the S3 by doing this rotation on the angles before attaching it again. So basically, it's like an S3 which is moving along the S1, but it's identified after a rotation with itself. So this manifold is locally the round S3 times S1, but not globally. And if you look at what the Killing vector, the holomorphic Killing vector in this case is, you find out that it's given by the following. Sorry, anthropomorphic, whatever. So indeed, it corresponds to moving along x with the real part, while the imaginary part is moving along one of fiber on the S3. And so given this information, you can actually figure out when this is compatible with having 4 supercharges. Because the theorem which allows for 4 supercharges, you find out as superalgebra, it has SU2/1 left times SU2 right times U1, where, so SU2 left times SU2 right is just the isometry of the 3-sphere. then the U1 corresponds to like moving along the S1, and the extra U1 here is the U1 asymmetry. The important thing is that all the supercharges are in SU2 left, and therefore doing these identifications is compatible with the supercharges only when these identifications are like not in the direction of the scaling vector, which is in the SU. So the imaginary part of the scaling vector is in the SU2 left. So it actually rotates the supercharges. So you don't want the identification to rotate the supercharges because otherwise it will break some supersymmetry. So the way to ensure that is to take theta p equals to minus theta q. And then this identification is in the other SU2 group under which the supercharges are invariant. So the identification preserves all four supercharges. And hence the result is that the only choice of P and Q for which four supercharges are kept is P equals Q star. So four supercharges imply P equals Q star. Okay, so now I will just conclude in the next 5 minutes by showing that this is enough to recognize like P and Q in the results which appeared in the literature.
Before you erase this, what is the theory change matrix? Is it constant or?
Of this one? Yeah. So if P is equal, if the absolute value of P is equal to the absolute value of Q, then the metric is locally, so this particular metric, which is compatible with the complex structure, is locally around the street of this one. So the curvature is, the curvature of this tree is constant, yes.
But even when P is not equal to,
no.
So Q you have something, yeah?
Yeah, so if P is not equal, if the absolute values of P and Q are not equal, then the round metric is not compatible with the complex structure.
And there is no supersymmetry.
No. So you can always have two supercharges, but not four.
Mm-hmm.
So the only case where you have four is P equal to star.
And do you have any examples where curvature is not constant?
Yes. All the cases where P is the absolute value of P is not equal to the absolute value of Q don't have constant curvature.
But then you have only one supercharge.
No, two supercharges. While the cases where, which are in the second branch only allow for one supercharge. And there the metric is actually pretty good. You can write down metrics, they are like quite...
Sorry, one more question. So the absolute value of P and Q are not the same. The change in coordinates you wrote there is also valid, right?
Yes, so indeed, so if the absolute value, so this is a little bit complicated, if the absolute value of P is equal to the absolute value of Q, it's compatible with the round metric, but it's not compatible with four supercharges. So four supercharges is more than just the round metric.
No, what I'm asking is that if that change of coordinates is always valid, then so is it
yes,
true
this,
that
yeah, this change of coordinate is okay as long as the absolute value of P and the absolute value of Q like are the same.
I thought this is true even when the absolute value of P and Q are not the same. You can always write like that, can't you?
Let me think a second. Yeah, but then, yes, but then these identifications don't correspond to the correct ones.
But is it true that for any value of P and Q, the manifold is diffeomorphic to S3 5 over S1?
That's always true. It's S3 times S1, but not around S3.
Okay.
This was perhaps a little bit rushed. So, okay, so the last thing I want to say is that people consider like the theory with four supercharges. And for this theory, which has the superalgebra we have here, one can compute an index. So this index is just given by the following. So it's the trace on the S3 of -1 to the F, where F is the Fermi number, times some object which I call P, which will become the P, but for now you don't know it's the same, times J3 plus J3 prime minus R over Q. So J3 and J3 prime are generators of the S2 left and S2 right. Perhaps we could write them left and right. Here. And then we have Q, J3 minus J3, so left and right, minus R over Q. So R is the R charge. So you compute this trace over all the states of your theory, and if you have some flavor symmetries, you could also introduce like chemical potentials for the flavor symmetry. So these are flavor charges. Okay, so you compute this, and because the superalgebra is this SU2/1 times SU2 times 1, what you get is the only states which contribute are the ones for which the eigenvalue corresponding to rotations around the S1 is equal to 2J3 left minus R. And therefore, given the fact that it's given in terms of the R charges and the eigenvalues of rotations around the S3, this index is protected. So like you can compute it in the EV of your theory, and then it's the same in the IR. And so now, if you take this object and you take it for P equals Q bar, you can rewrite it, and it just becomes, you can just rewrite it as e to the minus delta h, where h is the generator along the S1, plus qi delta J3 right. So here you recognize exactly the partition function of the theory on S3 times S1, where like as you move along the S1 of radius beta, you identify the sphere by a J3 right rotation in this SU2 right. So this is exactly the case we described corresponding to P equals Q star. So indeed, given the two results that from what we said, the dependence of the partition function should be holomorphic in the complex structure modular. So it should be holomorphic in P and Q. And also we can identify the section P equal Q star with P equal Q star in the Kodaira classification. So these two elements are enough to say that this index is actually a function of P and Q, as people have written. It's actually a function over the modular space of primary of surfaces. And then by dimensional reduction, we can get various results for almost complex structure in 3 spheres. But
questions?
So in the beginning we consider linear definition, linearized definition. If you look at full definition, what is the order of the equation you get for the definition? Is it order 2 or 3?
What do you mean?
If you don't linearize your equations, then in the definition.
Oh, you mean the right? So let me think. I think it's second order.
Second, okay. Then there is standard technique to
extend
the result by
The deformations of the complex structures have been looked in.
No. So if you look just at linear definition, then you have the statement in terms of cohomology.
Right.
But generally, you might overcount.
There are obstructions, but those have been studied by Kodaira and Spencer. So there is a theory. It's so for instance, for the case of Hopf surfaces, there are theories that these are the only those identified by Kodaira are the only complex structures on manifold diffeomorphic to this one. So in that case, actually,
Well, I think S3 times S1 has so many complex structures, and
well, not so many. Like it's 2 complex dimensional.
S3 times S1, it's what people call
more or less hypercurly, which has infinity in many complex structures. Well, that's for sure. This is definitely, it's in the literature. I mean,
Well, yeah, infinitely many. They are parameterized by two complex moduli, or there is another branch.
well, I mean, they're parameterized by two spheres, by two CT1s. I don't know.
Well,
Two
there's
CT1s.
two parameters.
Yeah, but that's okay.
There's nature.
Here it's two complex parameters.
Now, there are several, I think this is like completely classified. Those are the ones that I wrote. There is one branch which has two complex moduli, and one branch, and then there are an infinite number of branches parameterized by this integer n, each one of which is one complex dimension. So people have computed like the partition function corresponding to this like two-dimensional branch where you can actually preserve the supercharges, and they found these species. And in principle, one could think about computing the ones on the other branches.
Other questions? If no, let's thank